On October 4th, 2025, a photograph from Mars changed everything. Not gradually, not through careful scientific analysis conducted over months in sterile laboratories, but instantly. The moment that image hit the internet and collided with human curiosity, the Perseverance rover sitting in Jezero crater some 225 million kilometers from Earth had captured something in the Martian sky that would divide the scientific community and ignite a debate that continues to burn today. What appeared in those grainy black and white pixels was not the familiar circular dot of a distant comet, not the fuzzy blob with a streaming tail that we've grown accustomed to seeing in our textbooks and documentaries. Instead, what emerged from the stacked navigation camera images was something altogether different. An elongated, glowing object roughly 4 times longer than it was wide, hanging against the backdrop of space like a cosmic cigarette. Impossible to ignore, and even more impossible to explain away. Within hours, the internet had exploded. Reddit threads multiplied like digital wildfire, each comment section becoming a battlefield of interpretation. Twitter, that great amphitheater of human reaction, lit up with amateur astronomers, conspiracy theorists, professional scientists, and everyone in between, all trying to make sense of what they were seeing. YouTube channels rushed to analyze every pixel, to enhance contrast, to draw conclusions from data that was already being stretched to its limits. And at the center of this digital storm, 2 camps emerged with the clarity of ancient armies taking their positions on opposite sides of a battlefield. On one side stood Avi Loeb, the Harvard astrophysicist, whose name had become synonymous with asking uncomfortable questions about visitors from beyond our solar system. Loeb looked at the elongated appearance and saw a trick of physics, an artifact created by the marriage of a moving object and a camera's limitations. His explanation was elegant, mathematically sound, rooted in the kind of careful reasoning that has guided scientific inquiry for centuries. The object was moving, he argued. Moving fast. Over the 10 minutes it took to capture enough images for stacking, 3i at LS had traveled roughly 50,000 kilometers across the Martian sky. Stack those images together, and you get a time-lapse effect, the same phenomenon that turns car headlights into ribbons of light in a long-exposure photograph. On the other side, Dr. Horace Drew emerged as an unexpected challenger. His credentials were impeccable: work at Caltech, research at the MRC Laboratory of Molecular Biology in Cambridge, publications spanning molecular biology in more speculative territories. Drew looked at the same images and saw something that Loeb's explanation couldn't account for. If this was merely a camera artifact, if we were looking at a small rocky nucleus surrounded by a large green coma being smeared across multiple frames, then the color distribution was all wrong. The enhanced images showed something crucial that kept nagging at Drew's analytical mind. The center appeared white, brilliant, and distinct, while the edges showed that characteristic green tinge that astronomers associate with comet activity. But here's what troubled him. If you're stacking hundreds of images of a small nucleus surrounded by a much larger green cloud, the mathematics of light accumulation should overwhelm that central white region with green. There should be so much accumulated green light from the surrounding coma that the final image couldn't possibly maintain such a stark white center. Unless the white emitting region wasn't small at all. Unless it was large, extended, significant enough in size that when you stack the images, the white material outweighs the green material in each individual frame. Unless the object itself possessed an elongated white structure that was larger than the green coma surrounding it. The implications of Drew's observation rippled outward like stones thrown into still water. If the elongation wasn't an artifact, if it represented real physical structure, then humanity was looking at something unprecedented in our experience of interstellar objects, something that challenged every assumption we'd made about what wanders between the stars. But here's where the story takes its first truly strange turn, where coincidence begins to feel less like chance and more like orchestration. The timing was exquisite in its inconvenience. NASA's government shutdown had begun on October 1st, exactly 48 hours before 3i at LS made its closest approach to Mars. Thousands of NASA employees were furloughed. Websites weren't being updated. Press releases weren't being drafted. The agency, in its own carefully worded statements, was operating with minimal staff focused only on mission-critical activities. Processing and releasing images of an interstellar visitor, no matter how scientifically fascinating, apparently didn't qualify as mission-critical during a funding lapse. The coincidence felt almost surgical in its precision. Here was the most anticipated astronomical event in years, the closest approach of only the third confirmed interstellar object ever detected, occurring at the exact moment when the United States' premier space agency was effectively silenced by political dysfunction. It was either the cruelest irony in the history of space exploration, or it was something else entirely. But NASA's silence was only the beginning. The European Space Agency, operating completely independently of American budget politics, also remained silent. Their Mars Express orbiter had been positioned perfectly to observe the flyby. Their instruments had captured data. Their processing capabilities were unaffected by Washington's political theater. Yet no images emerged, no preliminary reports, no acknowledgement beyond brief confirmations that observations had been attempted. China added another layer to the mystery. The China National Space Administration, through their Tianwen-1 Mars orbiter, routinely releases images within 48 to 72 hours of capture. They've published over 14,000 images from Mars since arriving in orbit, often timed to coincide with national celebrations or to demonstrate their growing capabilities in space. When significant observations are made, China makes sure the world sees them immediately. It's a matter of national pride, of technological demonstration, of showing that they can achieve what others achieve. Yet, after October 3rd, nothing. No images of 3I@LS from Tianwen-1's cameras. No spectroscopic data. No press releases celebrating China's contribution to understanding this interstellar visitor. The silence was uncharacteristic, unprecedented, and deeply unsettling. The United Arab Emirates completed this quartet of inexplicable quiet. Their Hope probe, the Emirates Mars mission, represented a source of enormous national pride, the Arab world's first interplanetary mission, a technological achievement that had been celebrated extensively since its arrival at Mars in February 2021. The UAE Space Agency maintains an active social media presence. They regularly publish data, release updates, engage with the global scientific community. Hope's instruments were perfectly suited for studying 3I@LS, the Emirates Mars Infrared Spectrometer, and the Emirates Mars Ultraviolet Spectrometer could have provided crucial data about the comet's chemical composition, about how gases in its coma interacted with solar radiation. And Hope had a clear line of sight during the flyby. Yet, silence. Complete, total, unexplained silence. 4 space agencies, 4 nations that compete for prestige, funding, and influence in space exploration. 4 organizations that don't typically coordinate anything, that view each other as rivals on the world stage, all suddenly united in their refusal to share what their instruments had captured during the most significant astronomical event in recent memory. The silence became louder than any official statement could have been. It screamed across the internet, fueling speculation that ranged from reasonable to absurd. Because when official sources go quiet, when the authorities who are supposed to provide answers refuse to speak, people begin to wonder what those authorities might be trying to hide. And as 3I@LS continued its journey toward the Sun, racing toward its October 29th perihelion, at speeds that defied easy comprehension, the questions multiplied faster than the answers. What was this object that had traveled for billions of years to arrive in our solar system at this precise moment? What had those Mars orbiters actually seen during their closest observations? And why were 4 competing nations suddenly singing the same song of silence? Understanding what happened in those Perseverance images requires diving deep into the technical reality of how we actually capture photographs of objects millions of kilometers away. This isn't Instagram photography. This is precision engineering at the edge of what's physically possible, where every pixel carries information that might change our understanding of the universe. The Perseverance rover's navigation cameras weren't designed for astronomical observation. They're utilitarian instruments, built to help the rover avoid obstacles and plan routes across the Martian terrain. These cameras capture images in black and white, with an angular resolution of 33 milliradians per pixel. Those technical specifications mean very little until you translate them into human scale. At 3I@LS's distance of 38 million kilometers, each pixel represented roughly 12,500 kilometers of space. Think about that number for a moment. Each individual pixel in those images covered an area larger than Earth's diameter. You're not going to see fine details. You're not going to resolve surface features or count structural elements. What you might see, if you're very careful and very lucky, is the general shape of something, especially if you can combine multiple images to reduce noise and amplify real signals. And that's exactly what happened. Amateur astrophotographers monitoring NASA's raw image feeds began the painstaking process of image stacking. Not just 2 or 3 frames, but hundreds of individual images captured over approximately 10 minutes of Martian time. This stacking process is fundamental to modern astronomical photography. When you're trying to capture something faint, you combine multiple exposures. Random noise averages out, but real signals add up. It's how amateur astronomers capture nebulae with backyard telescopes, how professionals tease out the faintest galaxies at the edge of the observable universe. When those hundreds of frames were carefully aligned and combined, something emerged from the noise. Not the circular dot that every textbook tells us. Comets should appear as when viewed from great distances. Not the fuzzy, roughly spherical blob with a tail streaming behind it, like every comet humanity has ever observed from Earth. Instead, what appeared was a stripe, an elongated feature, roughly 4 times longer than it was wide, glowing against the background of space with an intensity that couldn't be ignored. Critically, this elongated feature showed a color distribution that would become the center of heated scientific debate. The center appeared white, brilliant, and distinct, while the edges showed hints of green, that characteristic emerald tinge that astronomers associate with carbon compounds fluorescing under solar ultraviolet radiation. Avi Loeb's explanation arrived with the mathematical precision that has characterized his entire career. The elongation, he argued, was purely an artifact of motion and time. 3I at LS was traveling at approximately 67 kilometers per second relative to the Sun, following a retrograde orbit that moved opposite to Mars's orbital direction. From Mars's perspective, the object was screaming across the sky at a relative velocity of roughly 91 kilometers per second when both motions were accounted for. Over 10 minutes, the object would travel approximately 54,000 kilometers. If you're stacking hundreds of individual frames taken during that time period, you're essentially creating an accidental time-lapse photograph. The object's motion gets smeared across the final image, creating the illusion of elongation. It's identical to photographing a car driving past at night with a long exposure. The car itself might be compact, but in the photograph it appears as a streak of light stretched across the frame. Loeb calculated the numbers with characteristic precision. The navigation camera's angular resolution meant each pixel covered 12,500 kilometers at 3I at L's distance. The stripe appeared roughly 50,000 kilometers long in the stacked image. Divide that by the object's velocity relative to Mars, and you get approximately 9 to 10 minutes, which perfectly matched the integration time needed to stack enough frames to bring the faint object above the noise threshold where it became visible. The mathematics checked out beautifully. The explanation was elegant, straightforward, grounded in well-understood principles of imaging and orbital mechanics. For most of the scientific community, this should have been case closed. Another mystery solved by careful analysis and proper understanding of instrumental effects. But Dr. Horace Drew wasn't satisfied with elegant mathematics when the observational evidence seemed to contradict them. Drew focused his attention on something that Loeb's explanation struggled to address: the color distribution in the enhanced images. The center of that elongated stripe appeared predominantly white, while the edges showed the green coloration consistent with ground-based observations of 3I at LS, showing a green nickel-rich coma. Drew's counterargument was geometrically rigorous. If the elongation was purely an artifact created by stacking images of a small rocky nucleus moving through a larger green coma, then combining those frames should result in the central stripe appearing predominantly green. Each individual frame would contain a small bright nucleus surrounded by a much larger, fainter green cloud. When you stack hundreds of such frames in sequence, following the object's motion, you're essentially adding up all that green light from every frame. The accumulated green emission from the extensive coma should overwhelm any white light from the small central nucleus. There would be so much green material in the final stacked image that maintaining a bright white center becomes mathematically problematic. The only way to preserve white dominance in the center while showing green at the edges would be if the white emitting region was significantly larger than initially assumed. This wasn't a subtle technical point. This was a fundamental question about the geometry and brightness distribution of the object itself. If Drew was correct, it suggested that 3I at LS possessed an extended white structure, what he described as an exile structure, that was physically larger than the green coma surrounding it. In that scenario, stacking the images would preserve the white dominance in the center because each individual frame contained more white-emitting material than green-emitting material. The debate revealed a deeper challenge in astronomical observation. We're not seeing these objects directly. We're seeing sunlight scattered by dust and gas, emission from atoms excited by solar radiation, reflected light from surfaces we can't resolve. Determining the true shape, size, and structure of a distant object from such indirect observations is fraught with assumptions and interpretations. Several astrophysicists who weren't directly involved in the Loeb-Drew exchange began running their own simulations. If you model 3I at LS as a point source and track how that point would appear to move across the Martian sky over 10 minutes, you can generate synthetic images, blur each position to account for the navigation camera's resolution, stack them, and see what you get. These simulations generally supported the artifact explanation. A moving point source, when tracked and stacked, produces an elongated streak whose length matches the distance traveled during the exposure time. But the simulations made critical assumptions. They assumed 3I at LS was essentially point-like, that its brightness was concentrated in a small nucleus. What if the coma was already extensive at that distance? What if it was dozens or hundreds of kilometers across? Then each frame wouldn't capture a point, but a fuzzy disk. Stacking fuzzy disks over time creates a different result than stacking points. The streak becomes smeared, less defined with a different brightness distribution. The sharpness of the edges in the actual images became another point of contention. The elongated feature showed relatively well-defined boundaries, sharper than many expected if they were looking at stacked images of a large, diffuse coma moving across the frame. That sharpness could suggest the coma was smaller than expected, that the nucleus was brighter relative to the coma, or that something about the structure was indeed elongated at the source. Multiple Mars orbiters from different countries had pointed their instruments at 3I at LS during the flyby. The Mars Reconnaissance Orbiter, Mars Express, ExoMars Trace Gas Orbiter, China's Tianwen-1, the UAE's Hope probe, all of them had captured data during the closest approach on October 3rd. These spacecraft carried instruments with significantly better resolution than Perseverance's navigation cameras. The high-rise camera aboard Mars Reconnaissance Orbiter could achieve 30 cm per pixel resolution at 3I at LS's distance. The spectroscopic instruments could reveal chemical composition. The color cameras could provide definitive answers about the brightness distribution that had sparked such heated debate. Yet as the scientific community waited for this higher quality data, as amateur astronomers continued their own observations and analysis, as the internet buzzed with theories and interpretations, the official sources remained silent. The raw Perseverance navigation camera frames were publicly available because NASA posts them automatically, but the processed, high-resolution images from professional astronomical instruments remained locked away behind the bureaucratic barriers of government shutdowns and institutional caution. That silence, more than any technical debate about pixel stacking and color distribution, became the real story, because in the absence of authoritative data, speculation flourished unchecked, and 3I at LS, whatever it truly was, had already proven itself unusual in ways that extended far beyond debates about photographic artifacts. There's something profoundly unsettling about silence when you're expecting noise. In our hyper-connected age, where space agencies compete for public attention and social media engagement, where every successful Mars landing generates immediate press releases and carefully choreographed photo streams, the coordinated quiet that followed 3I at LS's closest approach felt almost unnatural. To understand why this silence was so unprecedented, you need to grasp the normal rhythm of space exploration announcements. When China's Tianwen-1 captures images of Martian dust storms, those pictures appear on official channels within days, often accompanied by explanatory graphics and patriotic messaging about China's growing space capabilities. When ESA's Mars Express photographs seasonal changes in polar ice caps, those images become part of press packages highlighting European technological achievement. When NASA's rovers discover interesting geological formations, the images trend on social media with hashtags and educational content designed to inspire the next generation of scientists. This isn't altruism, it's institutional survival. Space agencies exist at the pleasure of governments that control their budgets. Public engagement translates to political support, which translates to continued funding. Every spectacular image, every scientific breakthrough, Every technological demonstration serves the dual purpose of advancing human knowledge and justifying taxpayer investment in space exploration. The discovery and close approach of 3I at LS should have been a perfect opportunity for every space agency involved to showcase their capabilities. Here was only the third confirmed interstellar object ever detected, making its closest approach to Mars in what might be a once-in-a-lifetime observational opportunity. The scientific value was obvious, the public interest was guaranteed, and the bragging rights were substantial for whichever agency produced the best images or most significant discoveries. Instead, silence. Not just from one agency, but from all of them simultaneously. And these weren't agencies that typically coordinate their communications or align their messaging. These were competitors, rivals, organizations representing nations with very different political systems and strategic interests. Consider China's track record in detail. The China National Space Administration has published over 14,000 images from the Tianwen-Hua's orbiter since it entered orbit in 2021. These aren't just raw data dumps uploaded to satisfy scientific obligations. They're carefully processed, aesthetically pleasing images released with accompanying press statements, often timed to coincide with national celebrations or to underscore China's growing capabilities in space. When Tianwen-1 captured a global color map of Mars at 76 meter per pixel resolution, the images were released within days. When the accompanying rover Zhurong landed on the Martian surface and began transmitting photos, China made sure the world saw them immediately. This pattern of rapid publication serves China's broader strategic goals. The space program is a source of national pride, a demonstration of technological competence, a way of showing that China can achieve what traditionally only the United States and Soviet Union could achieve. Every successful mission, every published image, every scientific result becomes part of a larger narrative about China's rise as a technological power. So when 3I at LS made its closest approach to Mars and Tianwen-1 had a perfect vantage point to observe it, the natural expectation was that China would rush their results to publication. Imagine the headlines: China captures unprecedented images of interstellar visitor. It's exactly the kind of scientific achievement that plays well both domestically and internationally, the kind that justifies funding and generates excitement. Instead, nothing. No images, no preliminary analysis, not even a brief statement confirming successful observations beyond the pre-flyby announcements. The silence was completely out of character for an agency that had never missed an opportunity to highlight its successes. NASA's silence was easier to explain, at least superficially. The United States government had entered a shutdown on October 1st, 2 days before the flyby. Thousands of NASA employees were furloughed. Websites weren't being updated with new content. Press releases weren't being drafted. The agency was operating with minimal staff focused only on activities deemed mission-critical for crew safety and asset protection. But this explanation had holes. The shutdown didn't prevent the Perseverance rover from continuing to post raw navigation camera images automatically. Those images were uploaded through systems that run without human intervention, part of the mission's automated data management protocols. If raw navigation camera images could still be posted during the shutdown, why couldn't raw high-rise images be uploaded? The technical infrastructure existed. The automated systems were functioning. More troubling was the timing. Government shutdowns don't happen randomly. They occur when budget negotiations fail, when Congress and the President can't agree on funding levels for federal agencies. The federal fiscal year ends on September 30th, so shutdown deadlines are predictable well in advance. Yet here was a shutdown beginning precisely 48 hours before the most anticipated astronomical event in recent memory. The coincidence felt almost surgical in its precision. Either the political dysfunction that led to the shutdown was completely independent of astronomical events, which it almost certainly was, or someone with knowledge of both budget negotiations. 3I at LAS's trajectory had recognized an opportunity to create plausible deniability for information restrictions. But timing coincidences can be genuine, and NASA's silence was only part of a larger pattern. The European Space Agency's quiet was harder to explain. ESA operates completely independently of American budget politics. Their funding comes from European governments, through a completely different political process. Their Mars Express and ExoMars Trace Gas Orbiter missions were both positioned to observe 3I at LS, and ESA had announced in September that observations would take place between October 1st and 7th. These weren't casual observations. They were planned, scheduled, coordinated efforts involving multiple teams across European nations. ESA had specified that Mars Express would use its high-resolution stereo camera and various spectrometers, while the Trace Gas Orbiter would employ its color and stereo surface imaging system and its own suite of instruments. For an agency that routinely shares spectacular images of Mars, that publishes results from its many missions with regularity, that maintains an active public engagement program, the absence of any 3I@Ls related releases felt deliberate. ESA had the capability, the positioning, and the institutional motivation to produce and share results. Their silence suggested either technical problems with all their instruments simultaneously, which seemed unlikely, or a conscious decision not to share what they had captured. The United Arab Emirates added yet another layer to the mystery. Their Hope orbiter represents enormous national pride. The Emirates Mars mission was the Arab world's first interplanetary mission, a technological achievement that demonstrated the UAE's growing capabilities in space exploration. The mission team regularly publishes data, releases updates, and engages with the international scientific community. The UAE Space Agency maintains an active social media presence celebrating their achievements. Hope's instruments were actually ideal for studying 3I@Ls, the Emirates Mars Infrared Spectrometer, and the Emirates Mars Ultraviolet Spectrometer could provide crucial data about the comet's chemical composition, about how gases in its coma interacted with solar radiation, about the temperature distribution, and molecular signatures that might resolve some of the puzzles about its unusual chemistry. Yet, after October 3rd, nothing. No images of 3I@Ls from Hope's cameras, no spectroscopic data from its instruments, no press releases celebrating the UAE's contribution to understanding this interstellar visitor. The silence was completely out of character for a mission and agency that had never missed an opportunity to showcase their achievements. When observers began pointing out this coordinated silence across geopolitical lines, some interesting historical parallels emerged. There have been moments when rival nations cooperated on matters of mutual interest despite broader conflicts. The Partial Nuclear Test Ban Treaty of 1963 was signed by the United States, Soviet Union and United Kingdom at the height of the Cold War because atmospheric nuclear testing threatened everyone regardless of political ideology. Space rescue agreements followed, recognizing that astronauts and cosmonauts faced common dangers that transcended national boundaries. The Apollo-Soyuz test project in 1975 saw American and Soviet spacecraft dock in orbit, with crews shaking hands in space while their nations remained in ideological opposition on Earth. The common thread in these examples was shared existential stakes. When something threatens everyone equally, or when something affects the entire species, rivalry becomes secondary to survival or understanding. The 1998 United Nations Office for Outer Space Affairs established guidelines, though not binding treaties, about how nations should handle the detection of extraterrestrial intelligence. These protocols emphasize that no single nation should make unilateral announcements about potential contact. Confirmation should be verified through multiple independent sources. The international community should be informed through established channels. Premature disclosure could cause panic, misinformation, or international incidents. If the Mars orbiters had observed something that genuinely challenged the assumption that 3I@Ls was a natural object, you could construct a scenario where coordinated silence makes sense. Not as conspiracy, but as protocol, as caution, as an attempt to verify findings before making statements that couldn't be retracted. But that scenario requires believing something extraordinary was observed. And extraordinary claims require extraordinary evidence. The silence alone wasn't evidence of anything except that images hadn't been released. There could be mundane explanations that had nothing to do with the nature of 3I@Ls itself. Data processing takes time, especially for complex astronomical observations. Quality control requires careful review by multiple experts. Scientists often prefer to publish findings in peer-reviewed journals rather than through press releases to maintain credibility and priority of discovery. Institutional bureaucracy can delay releases even when the science is straightforward, yet the pattern remained troubling. 5 space agencies representing different continents, different political systems, different funding structures, all with functioning Mars missions, all positioned to observe the same event, all choosing not to share results in the immediate aftermath. 5 agencies that don't typically coordinate, that compete for prestige and scientific recognition, suddenly aligned in their silence. The internet took notice. Reddit threads accumulated hundreds of comments analyzing every angle. People noted that Tianwen-1 routinely posted images within 48 to 72 hours of acquisition. They pointed out that ESA had shared Mars Express images just days after capture in previous instances. They highlighted that the UAE's HOPE mission had a public data portal specifically designed for transparency and community engagement. Someone observed that on October 1st, just 2 days before the flyby, China's Tianwen-2 mission, an entirely separate spacecraft en route to collect samples from an asteroid, released a selfie image showing Earth in the background. It was a propaganda piece, beautifully composed, showing China's flag on the spacecraft with our planet as backdrop. The timing struck observers as significant. China was perfectly capable of releasing space images during the exact time frame when 3I@LS observations should have been processed. They chose to release a Tianwen-2 image. They chose not to release Tianwen-1 observations of the interstellar visitor. The silence spawned theories across the spectrum of possibility. Some argued that all the agencies saw nothing remarkable, that 3I@LS appeared exactly as expected for a comet, and thus there was no urgency to rush results to press when papers could be written properly through normal academic channels. But that didn't explain why China wouldn't leverage even mundane observations for prestige, or why the UAE wouldn't use the opportunity to showcase HOPE's capabilities. Others suggested technical failures, but perhaps all the instruments malfunctioned simultaneously, or that data corruption prevented meaningful analysis. But the odds of multiple independent systems failing at the same time seemed vanishingly small, especially when these were proven instruments that had been operating reliably for years. The more provocative theories suggested deliberate suppression, that high-resolution images had revealed structure, geometry, or characteristics that couldn't be easily explained as natural phenomena. That spectroscopic data showed chemical signatures inconsistent with any known comet, that multiple agencies recognized they were looking at something that required careful coordination to announce properly, if it was announced at all. One blogger compiled a timeline showing that in the 72 hours after the October 3rd flyby, various government officials and scientists had appeared on news programs discussing 3I@LS, that White House officials were being asked about an astronomical object, that it had risen to the level of potential presidential briefings, suggested this was being taken seriously at levels beyond just scientific curiosity. The fact that congressional representatives were appearing on television to discuss it, that questions about 3I@LS were being directed to White House staff, that the media was covering it as a developing story rather than just a science curiosity, all pointed to an event that had transcended typical astronomical observations. And yet, the core data remained locked away. The HARIS images capable of resolving features 30 kilometers across at 3I@LS's distance during closest approach would show whether the brightness came from a compact nucleus or something more extended. They would reveal actual structure if structure existed. They would put to rest or intensify the debates about elongation, about shape, about what this object fundamentally represented. Those images existed. They had been captured. Somewhere in databases and servers that had survived government shutdowns and institutional caution, the highest resolution photographs of an interstellar object ever taken by human instruments were sitting, processed, or awaiting processing, while the world waited for answers that never came. Color in astronomy isn't just aesthetics. It's information encoded in wavelengths of light, each hue telling a story about composition, temperature, and the physical processes occurring millions of kilometers away. When 3I@LS appeared reddish in July, and then transformed to green by September, it wasn't simply changing clothes for different seasons. It was advertising a fundamental shift in its chemistry, its activity level, and possibly its very nature. The James Webb Space Telescope had been tracking 3I@LS since early August, its infrared spectrographs dissecting the comet's light with precision that would have been impossible just a generation ago. What Webb revealed challenged everything astronomers thought they knew about interstellar comets and raised questions that no natural formation process could easily answer. Most comets are essentially dirty snowballs, remnants from the formation of planetary systems where water ice dominates the composition. When these objects approach the Sun, water sublimates off their surfaces, creating the characteristic tails and comas that have inspired human imagination for millennia. The chemistry is predictable: water vapor, with smaller amounts of carbon dioxide, carbon monoxide, and trace amounts of more exotic molecules. 3I at LS shattered that template completely. Webb's spectroscopic analysis revealed that the coma was dominated by carbon dioxide, not just enriched in CO2 but overwhelmingly composed of it. 87% carbon dioxide by mass, 9% carbon monoxide, and only about 4% water. That 8-to-1 ratio of carbon dioxide to water was so extreme it fell off the charts of known cometary compositions. Solar system comets typically show the opposite ratio, with water vastly outweighing carbon dioxide. Even comets from the outer reaches of our solar system, from the Oort cloud where temperatures are barely above absolute zero, show much more water than 3I at LS was displaying. The only other interstellar comet we'd studied, 2I/Borisov, had shown water-dominated chemistry similar to familiar solar system objects. Why was 3I at LS so dry? Natural explanations existed, but they required invoking special circumstances that strained credibility. Perhaps it had formed in an exceptionally cold region of its home star system, so far from its parent star that water ice had been depleted early in its history, while carbon dioxide remained stable. Or perhaps billions of years wandering through interstellar space had allowed cosmic rays to alter its surface composition, selectively destroying water-bearing minerals while leaving carbon compounds intact. These explanations were possible, but they painted 3I at LS as a profoundly unusual object even by the standards of interstellar visitors. If interstellar comets were supposed to provide us with samples of other planetary systems, with clues about how those distant worlds had formed and evolved, then 3I at LS was telling us about star systems fundamentally different from our own. But the chemical anomalies didn't stop with the extreme carbon dioxide dominance. Observations from the Very Large Telescope in Chile had detected something even more puzzling: nickel atoms streaming away from the comet at rates that defied conventional understanding of how metals behave in space. Nickel itself isn't shocking in comets. Many comets show trace metals in their spectra when they get close enough to the sun for high-temperature sublimation to occur. What was shocking about 3I at LS was the rate of nickel production. Critically, what was missing alongside it. In nature, nickel and iron are inseparable siblings. They form together in the cores of dying stars, get blasted into space together during supernova, and condense into planets and asteroids together in consistent ratios. Every rock sample we've ever analyzed from space, every meteorite that's fallen to Earth, every asteroid we've studied up close, shows nickel and iron appearing together in predictable proportions. They're chemically similar elements that bond to similar materials under similar conditions. Finding nickel without corresponding iron in natural processes is like finding hydrogen without the possibility of oxygen. Theoretically possible under very specific conditions, but so unusual that it demands extraordinary explanation. The Very Large Telescope data showed 3I at LS producing nickel emission lines without corresponding iron signatures. As the comet moved closer to the sun, nickel production increased dramatically while iron remained below detection limits. It wasn't until 3I at LS came within 2.64 astronomical units of the sun that iron finally appeared in the spectra, and even then the nickel-to-iron ratio remained far higher than any solar system comet or the previous interstellar visitor. 2I/Borisov. The researchers described this separation as extremely puzzling, which in the careful language of peer-reviewed astronomy papers translates to, "We've exhausted conventional explanations and are entering territory where new physics or chemistry might be required." How do you separate nickel from iron? On Earth, we've been doing it industrially for over a century. The Mond process, developed in the 1890s, uses carbon monoxide to form nickel carbonyl, a volatile compound that boils at just 43 degrees Celsius. You heat nickel-bearing ore with carbon monoxide at moderate temperatures. Nickel reacts to form gaseous nickel carbonyl, while iron compounds remain solid. You collect the gas and heat it to higher temperatures, where it decomposes back into pure nickel metal and carbon monoxide that can be recycled. It's how we make high-purity nickel for electronics, for corrosion-resistant alloys, for the nickel plating that protects steel components in harsh environments. It's standard industrial chemistry, perfected over decades, described in metallurgy textbooks worldwide, and it appeared to be happening naturally on 3I at LS. The comet had abundant carbon monoxide, 9% of its composition according to Webb observations. If it also contained nickel-bearing minerals in the right forms, solar heating could potentially drive reactions that form nickel-carbonyl compounds. These volatile molecules could sublimate at much lower temperatures than metallic nickel or nickel silicates, explaining why nickel emission appeared while the comet was still relatively far from the Sun. Iron could remain bound in different minerals that didn't form analogous volatile compounds under the same conditions. Iron carbonyl exists and is used in some industrial processes, but it requires different formation conditions than nickel carbonyl. If the mineralogy of 3I at LS was structured just right, with nickel preferentially available in forms that could react with carbon monoxide, while iron remained locked in more stable compounds, you could theoretically achieve the observed separation. But that explanation required stacking a series of improbable assumptions. The comet would need very specific mineralogical composition, unlike anything seen in solar system objects. The nickel would need to be present in forms that readily reacted with carbon monoxide. The iron would need to be sequestered in compounds that remained stable under the same heating conditions. And all of this would need to be common enough that an interstellar comet would naturally exhibit these properties. The alternative explanation was more straightforward but far more unsettling. If 3I at LS wasn't a natural comet but rather an artificial object designed to look like one, then the nickel signature made perfect sense. Nickel alloys are extensively used in spacecraft construction, favored for components that must endure radiation, extreme temperatures, and corrosive environments. Fuel tanks are often nickel-plated. Structural elements use nickel steel or nickel titanium alloys. Electronic shielding incorporates nickel-based materials. Even the Mars rovers rolling across the Martian surface use nickel in their wheel mechanisms, their joints, their thermal protection systems. If 3I at LS had a metallic hull or structural framework, solar heating as it approached the Sun would cause surface materials to outgas. Protective coatings would vaporize. Any volatile compounds on the surface, including those used for thermal control or as anti-corrosion treatments, would sublimate and show up in spectroscopic observations. The steep power law relationship governing nickel production added weight to this technological interpretation. As 3I at LS moved from 3.9 to 3.1 astronomical units from the Sun, nickel production increased by a factor of 25. The emission rate scaled with solar distance raised to the power of 8.43, an extraordinarily steep relationship that suggested threshold effects rather than simple thermal sublimation. Simple heating of surface materials typically follows much gentler curves. You'd expect nickel production rates to scale with distance raised to the power of -2 or -4, following the inverse square law of solar heating. A power of 8.4 suggests something more complex. Perhaps layers of insulating material protecting metallic surfaces underneath, with rapid exposure and heating once protective barriers were breached. Imagine a probe covered with accumulated interstellar dust and ices after billions of years of travel. As solar heating intensifies, the outer protective layers sublimate first, but underneath, metallic structural elements remain insulated. Then at a critical temperature threshold, the insulation becomes thin enough that heat penetrates to the metal surface. Once that happens, the metal itself begins heating rapidly, and any volatile compounds associated with it start vaporizing at accelerating rates. The sharp transition from protected to exposed, from cold to hot, from inactive to outgassing, would naturally produce the kind of steep power law relationship observed in the data. It would look like something activating rather than something passively warming up. The color change from red to green added another layer to the chemical mystery. Red coloration in distant objects typically indicates dust particles reflecting sunlight with a slight bias toward longer wavelengths. This made sense for 3I at LS when it was far from the Sun, and outgassing was minimal, predominantly dust being gently released from a slowly warming surface. Green comets are common enough that astronomers have standard explanations. Diatomic carbon molecules form when larger carbon-containing compounds get broken apart by solar ultraviolet radiation. These C2 molecules absorb UV light and re-emit it at specific wavelengths in the green part of the spectrum, around 510 nanometers. It's a beautiful process, and so predictable that detecting green emission usually means detecting carbon chain molecules. But when scientists obtained detailed spectra of 3I at LS during its green phase, they found an extremely low ratio of diatomic carbon to other carbon compounds. The molecule responsible for green coloration in most comets was essentially absent. It was like seeing smoke without fire, hearing music without instruments. Several teams suggested that cyanogen, the CN radical formed from carbon and nitrogen, might be responsible for the green appearance. Cyanogen can produce blue-green emission under certain conditions, and 3I at LS was showing steep increases in cyanogen production that followed power laws similar to the nickel emissions. But explaining green coloration through cyanogen required 3I at LS to have unusual nitrogen-to-carbon ratios compared to typical comets. Why would an interstellar object be simultaneously depleted in carbon chains but enriched in nitrogen-bearing molecules? What formation process or evolutionary history would create such a specific imbalance? If you were designing a probe for interstellar travel, you might use nitrogen-based propellants or coolants for attitude control or thermal management. Leaks or deliberate releases of these materials as the probe warmed up near a star could produce cyanogen as nitrogen compounds interacted with solar radiation. The steep power law increase in CN production could represent systematic activation of thermal management systems as solar input exceeded design thresholds. This remained speculation without direct evidence, but the pattern of chemical anomalies was becoming difficult to ignore. Carbon dioxide dominance without water, nickel without iron, green coloration without the expected molecules. Each anomaly might have natural explanations, but the combination was starting to feel like more than coincidence. As 3I at LS continued toward its October 29th perihelion, the chemical signatures promised to intensify. If the power laws held, if the relationships discovered by ground-based telescopes continued their steep curves, perihelion would trigger outgassing events that dwarfed anything observed so far. Whatever was causing these anomalous emissions would be subjected to maximum solar energy input, maximum thermal stress, maximum activation potential. The answers, if they existed, were racing toward us at 60 kilometers per second. When the Very Large Telescope in Chile pointed its sophisticated instruments at 3I at LS, the astronomers weren't expecting to encounter what amounted to a chemistry lesson in industrial metallurgy playing out millions of kilometers from Earth. They were looking for the familiar signatures of water, carbon dioxide, perhaps some trace metals, the standard composition that decades of cometary observation had taught them to expect. Instead, they found themselves staring at emission spectra that looked less like a natural comet and more like the exhaust from a specialized manufacturing process. The UVIS spectrograph, with its ability to detect incredibly faint emission lines from excited atoms, had been tracking the metal content of 3I at LS since July. Metal detection in comets requires extraordinary sensitivity, because the temperatures needed to vaporize mineral grains typically only occur when objects get very close to the sun. Most comets don't reach the 1000-degree Kelvin threshold needed for significant metal sublimation until they're well inside Earth's orbit. 3I at LS was different. It was producing detectable metal emissions when it was still 3.9 astronomical units from the sun, more than 3 times farther than Earth's distance from our star. At that range, solar heating should be weak, insufficient to vaporize the silicate minerals that contain metals in typical rocky bodies. Yet there were the emission lines, clear and unmistakable, growing stronger with each passing week. What made this discovery even more remarkable was the rate of increase. Between late July and late August, as 3I at LS moved from roughly 3.9 to 3.1 AU from the sun, the nickel production rate didn't just increase, it exploded. 25 times more nickel atoms were being released per second after just 1 month of closer solar approach. The team led by Rohan Rahat Gon modeled this increase, and found it followed a power law with an exponent of 8.43 plus or minus 0.79. In simpler terms, the production rate was exquisitely sensitive to distance from the sun. Move even slightly closer, and nickel emission jumped dramatically. This wasn't the gentle increase you'd expect from gradually warming ice. This was explosive, threshold-driven behavior that suggested something fundamentally different was happening. For comparison, water sublimation from typical comets follows power laws with exponents around -2, directly related to the inverse square law of solar heating. Carbon dioxide sublimation might show exponents around -4 as temperature-dependent chemical processes become more efficient. But 8.4? That level of sensitivity to solar distance implied processes that remained dormant until critical thresholds were reached. then activated rapidly once those barriers were crossed. The iron problem compounded the mystery exponentially. Every sample of cosmic material ever analyzed by humanity shows nickel and iron appearing together. They're forged together in stellar cores, dispersed together in supernova explosions, condensed together in planetary formation processes. In meteorites, asteroids, and planetary samples, the nickel-to-iron ratio varies within predictable bounds, but both elements are always present. Finding nickel without iron in natural space materials is so unusual that it challenges fundamental assumptions about how matter behaves in cosmic environments. It's not impossible. Under very specific conditions, you might imagine scenarios where chemical processes could separate these normally inseparable elements, but it requires invoking circumstances so extraordinary that they demand exceptional evidence. The UV's observations showed exactly this impossible separation. Early in the observing campaign, iron emission lines were completely absent, while nickel blazed brightly in the spectra. It wasn't until 3I at LS came within 2.64 AU that iron finally appeared, and even then the nickel-to-iron ratio remained far higher than any known solar system object. On Earth, separating nickel from iron is routine industrial chemistry, so well understood and widely practiced that the processes are described in undergraduate metallurgy textbooks. The Mond process, developed in the 1890s by Ludwig Mond, exploits the fact that nickel readily forms volatile compounds with carbon monoxide, while iron remains largely inert under the same conditions. The process is elegantly simple. Heat nickel-bearing ore with carbon monoxide to around 50–80 degrees Celsius. Nickel reacts preferentially to form nickel-carbonyl NiTO4, a gas that boils at just 43 degrees Celsius. Collect this gas, separate it from the solid residue containing iron and other metals, then heat the nickel-carbonyl to 150–200 degrees Celsius, where it decomposes back into pure nickel metal and carbon monoxide that can be recycled. This industrial process produces the high-purity nickel used in electronics manufacturing, corrosion-resistant alloys, and specialized coatings. It's how we make the nickel plating that protects steel components from rust, the nickel-based superalloys used in jet engines and spacecraft, the pure nickel wire used in precision instruments, and remarkably, the conditions required for this process seem to exist naturally on 3I at LS. The comet contained abundant carbon monoxide, 9% of its total composition according to Webb Space Telescope observations. Solar heating could potentially drive reactions between CO and nickel-bearing surface materials, forming volatile nickel-carbonyl compounds that would sublimate at relatively low temperatures and show up as emission lines in astronomical spectra. Meanwhile, iron could remain bound in silicate minerals or oxide compounds that don't form volatile carbonyls under the same conditions. Iron carbonyl exists and is used in some industrial applications, but it requires higher temperatures and more specific chemical environments than nickel carbonyl. If the surface composition of 3I at LS was structured appropriately, you could imagine natural processes that mimicked industrial nickel refinement. But this natural explanation required a remarkable series of coincidences. The comet would need exactly the right mineralogical composition, with nickel present in forms that readily reacted with carbon monoxide, while iron remained sequestered in more stable compounds. The surface would need to maintain the proper temperature and chemical conditions for nickel-carbonyl formation, while suppressing iron-carbonyl production. And all of this would need to be common enough that an interstellar comet would naturally exhibit these properties, despite interstellar objects being incredibly rare in our experience. The alternative explanation was more direct, but carried implications that made many scientists uncomfortable. If 3I at LS wasn't a natural comet, but rather an artificial object designed to appear comet-like during casual observation, then the nickel signature made perfect engineering sense. Spacecraft construction relies heavily on nickel-based materials because of their exceptional properties under the extreme conditions of space travel. Pure nickel and nickel alloys resist corrosion from atomic oxygen, maintain strength across wide temperature ranges, and provide excellent shielding against both electromagnetic and particle radiation. The fuel tanks of satellites are often lined with nickel or nickel-plated steel to prevent contamination and corrosion. Structural frameworks use nickel-steel alloys or nickel-titanium shape memory alloys that can survive thermal cycling from -200 degrees Celsius in Earth's shadow to +200 degrees C in direct sunlight. Electronic components are housed in nickel-plated enclosures that provide electromagnetic shielding while resisting environmental degradation. Even the Mars rovers currently exploring the Martian surface incorporate nickel throughout their designs. Their wheels use nickel-plated aluminum. Their joints and mechanisms contain nickel-bearing steels and superalloys. Their electronic systems are protected by nickel-based shielding materials. If 3I@LS possessed a metallic hull or structural framework designed for interstellar travel, solar heating would inevitably cause surface materials to outgas as the object approached the Sun. Protective coatings applied during manufacturing or accumulated during billions of years in space would begin to sublimate. Thermal cycling as the object rotated, or as different surfaces received varying solar exposure, would stress material boundaries and release trapped compounds. Any nickel-based materials on the surface, whether structural elements or protective coatings, would contribute to the observed emission spectra. The steep power law relationship could emerge naturally from threshold effects as solar heating penetrated through protective layers to reach metallic substrates underneath. Consider the thermal history of an interstellar probe. After billions of years traveling through space at temperatures barely above absolute zero, the object would be thoroughly cold-soaked. Any volatile materials on its surface would be frozen solid. As it entered a solar system and began receiving significant solar radiation for the first time in eons, heating would be gradual at first. Outer layers of accumulated interstellar dust and frozen volatiles would sublimate first, but beneath them metallic structural elements would remain protected. Then, at some critical solar distance, the insulating layers would become thin enough for heat to penetrate to the metal surface itself. Once that threshold was crossed, heating would accelerate rapidly as dark metallic surfaces absorbed solar radiation more efficiently than the lighter-colored ices they replaced. This threshold effect would naturally produce the steep power law relationships observed in the data. Below the critical distance, minimal metal emission as the surface remained protected. Above it, rapidly increasing emission as more metallic surface became exposed and reached sublimation temperatures for surface compounds and coatings. The behavior would look like activation rather than passive thermal response, like something designed to remain dormant during the cold journey between stars, then come alive when bathed in the energy of a new solar system. Temperature calculations supported this interpretation. Even at 2.1 AU from the Sun, simple thermal models predicted surface temperatures around 200 Kelvin for a slowly rotating object with typical asteroid-like properties. That's far below the roughly 1000 Kelvin needed to sublimate silicate minerals containing nickel, yet nickel was being produced efficiently at those distances. Either the surface was much hotter than thermal models predicted, perhaps due to some greenhouse effect or internal heat source, or the nickel wasn't coming from direct sublimation of minerals, but from some other process operating at lower temperatures. Nickel-carbonyl formation could work at the observed temperatures, which is why it became the favored natural explanation among astronomers trying to avoid more speculative interpretations. But the technological explanation remained simpler and more complete. Spacecraft materials outgassing under solar heating required no exotic chemistry, no unusual mineral compositions, no remarkable coincidences of formation history. It required only that humanity had encountered a manufactured object rather than a natural one. The cyanogen production added another piece to the puzzle. CN radicals were being produced at rates that followed an even steeper power law than nickel, with production scaling as distance to the power of 9.38. If you were trying to explain both emissions through natural processes, you needed chemical environments that could produce both nickel, carbonyl, and cyanogen in rapidly increasing amounts with slightly different but consistently steep dependencies on solar heating. Cyanogen formation typically requires nitrogen-bearing compounds being broken apart by ultraviolet radiation. In a natural comet, you might expect this from ammonia ice or organic compounds containing carbon-nitrogen bonds. But the steep production curve suggested something more systematic than random photodissociation of surface ices. If 3I@LS employed nitrogen-based propellants or coolants for attitude control or thermal management, both common in spacecraft design, then controlled releases or system leaks as the probe warmed could produce the observed CN emissions. Nitrogen compounds reacting with solar radiation would form cyanogen radicals that would show up clearly in optical spectra. The pattern of chemical emissions painted a picture that was becoming difficult to ignore. Industrial-grade nickel separation, nitrogen compound releases following precise mathematical relationships, threshold-activated behavior, suggesting dormant systems coming online. Exotic chemistry that happened to match what you'd expect from technological materials under thermal stress. Each observation could potentially be explained through natural processes, but the explanations required stacking improbable assumptions about formation conditions, chemical environments, and evolutionary histories that had no precedent in our understanding of how interstellar objects should behave. As October 29th approached and 3I at LS raced toward perihelion, the metal emissions promised to reach their peak intensity. If the power laws held, if the mathematical relationships continued their steep curves, the nickel and cyanogen production rates would increase by additional orders of magnitude during the final approach to the Sun. That moment of maximum solar heating, maximum thermal stress, maximum potential activation, would either confirm the natural interpretations through familiar comet-like behavior, or it would push the anomalies so far beyond normal parameters that even the most conservative astronomers would be forced to consider alternatives they'd previously dismissed. The answers were accelerating toward us at interstellar speeds, carrying with them the potential to rewrite our understanding of what wanders between the stars. Mathematics has a way of cutting through speculation and forcing uncomfortable conversations about probability and coincidence. When Avi Loeb published his analysis of what he called the 7 anomalies of 3I at LS, he wasn't making emotional arguments or appealing to wonder about the mysteries of space. He was doing something much more unsettling. He was calculating the odds. Science deals with uncertainty by quantifying it, by assigning probabilities to different explanations and following the mathematics wherever it leads. When you encounter something unusual, you ask, what are the chances this happened naturally? What are the odds that random processes could produce this particular combination of observations? And when those odds become vanishingly small, you're forced to consider alternatives that might initially seem even more improbable. The first anomaly concerned the fundamental question of size and detectability. When 3I at LS was discovered in July, astronomers measured its brightness and worked backward to estimate its physical dimensions. If you assume the object reflects about 5% of incoming sunlight, a typical albedo for asteroids and cometary nuclei, then its observed brightness implies a diameter of roughly 20 kilometers. 20 kilometers is enormous for an interstellar object. Oumuamua, the first confirmed interstellar visitor, was estimated at around 100 meters across, roughly the length of a football field. 2I/Borisov, the second interstellar comet, measured approximately 1 kilometer in diameter. Now here was 3I at LS, potentially 20 times larger than Borisov and 200 times larger than Oumuamua. The problem isn't just that large interstellar objects are rare, it's that they should be exponentially rare. Planetary systems don't eject their biggest members easily. When planets form and gravitational interactions scatter objects outward during system evolution, it's the smaller bodies that get kicked out first. The larger an object, the more gravitational binding energy it has to its home system, the more energy required to accelerate it to escape velocity. Loeb calculated that if 3I at LS really is 20 kilometers across, detecting it within just a few years of continuous sky surveys implies a population density of large interstellar objects that exceeds what stellar and planetary formation models can support. The Milky Way would need to be producing and ejecting massive planetary building blocks at rates far higher than the available raw materials and energy sources allow. The alternative interpretation, that most of the observed brightness comes from an extensive coma of dust and gas surrounding a much smaller nucleus, resolves the size problem but amplifies the chemical anomalies we've already discussed. You can't have it both ways. Either 3I at LS is impossibly large for a natural interstellar object, or it's exhibiting impossibly unusual chemistry for a natural comet. The second anomaly emerged from Hubble Space Telescope observations in July that revealed something completely contrary to normal comet behavior. Instead of the expected tail pointing away from the Sun, 3I at LS showed a forward jet, a bright extension pointing toward the Sun rather than away from it. This anti-tail behavior isn't entirely unknown in solar system comets, but it typically results from specific geometric effects that are temporary and viewing angle dependent. What made 3I at LS unusual was the persistence and extreme nature of this forward-pointing emission. Loeb and his colleague Eric Quito analyzed the Hubble images and found that the sunward extension was roughly 10 times longer than the perpendicular or anti-sunward emissions. When corrected for viewing geometry, this 10:1 ratio became even more extreme. Forward jets can occur when volatile materials sublimate preferentially from the sun-facing hemisphere and are expelled with enough velocity to momentarily overcome radiation pressure. But sustaining such extreme asymmetry requires very specific conditions and very active outgassing patterns that don't match typical cometary behavior. The third through sixth anomalies all concern the trajectory itself, and this is where the statistics became genuinely uncomfortable. 3I at LS entered our solar system on a retrograde orbit, moving opposite to the direction planets orbit the Sun. Its orbital plane is tilted by only about 5 degrees relative to the ecliptic, the plane in which Earth and most planets orbit. 5 degrees doesn't sound significant until you consider the three-dimensional nature of space. If interstellar objects arrive from truly random directions, which they should, since there's no reason for them to preferentially approach from any particular angle, then the probability of an orbit being within 5 degrees of our solar system's planetary plane is roughly the solid angle of that narrow zone, divided by the total solid angle of a sphere. The calculation yields approximately 0.2%, or 1 chance in 500. Not impossible, but distinctly unlikely. The ecliptic plane is special to us because it's where our planets happen to orbit, but it has no particular significance in interstellar space. So why would this visitor from another star system be aligned with our local planetary configuration? Then consider the close approaches. 3I at LS passed within 29 million kilometers of Mars on October 3rd. Its trajectory will bring it relatively close to Venus, and it will encounter Jupiter at modest distance in March 2026. These aren't impact trajectories or even particularly close flybys by astronomical standards, but they're closer than statistical expectations for random arrivals. Loeb calculated the probability that an interstellar object entering on a random trajectory would happen to pass near multiple major planets. Using reasonable definitions of close approach distances, the combined probability comes out to roughly 0.005%, or 1 chance in 20,000. But the timing makes it even more improbable. Planets orbit at different speeds and spend most of their time far from any given point in space. Mars takes 687 days to complete one orbit. Jupiter requires almost 12 years. Venus needs 225 days. The probability that an interstellar visitor would arrive not only on a trajectory that passes near multiple planets, but also at precisely the right times when each planet happens to be positioned for close encounters. That probability multiplies the already low odds by additional factors. Loeb's rough estimate for the combined probability of both trajectory alignment and timing optimization came out to approximately 0.0005%, or 1 chance in 200,000. These aren't impossible odds. They're roughly equivalent to being struck by lightning in any given year. Lightning strikes happen, people win lotteries despite 1,000,000-to-1 odds. Unlikely events occur regularly in a universe as large as ours. But you start to wonder when unlikely events keep accumulating in the same object. Each additional coincidence makes the natural explanation more strained, more dependent on remarkable luck rather than ordinary physics. The seventh anomaly was perhaps the most speculative but also the most intriguing from a historical perspective. When astronomers traced 3I at LS's trajectory backward into interstellar space, they found that its arrival direction came from a region of sky in Sagittarius, roughly 9 degrees away from the origin of one of the most famous unexplained signals in the history of radio astronomy. On August 15, 1977, the Big Ear radio telescope at Ohio State University detected a strong narrowband signal that lasted exactly 72 seconds. The signal appeared at 1,420 MHz, the natural emission frequency of neutral hydrogen, a frequency that many SETI researchers consider a logical choice for interstellar communication, because any technological civilization would be familiar with this fundamental transition. The signal was so unusual, so apparently artificial in its characteristics, that astronomer Jerry Eman wrote "Wow" next to it on the computer printout. Despite decades of follow-up observations and analysis, the "Wow" signal has never been detected again, never been explained satisfactorily, and remains one of the most tantalizing potential evidence for extraterrestrial intelligence. Is it meaningful that 3I at LS's trajectory, when traced backward through space and time, points to within 9 degrees of the "Wow" signal's apparent origin? Loeb calculated the probability of this directional alignment as roughly 0.6%, better odds than some of the other coincidences. but still statistically unlikely. The connection requires believing that both the 1977 radio signal and the 2025 interstellar object represent artificial phenomena from the same source, a leap that goes far beyond what the data directly supports. But the alignment exists, it's documentable, and it adds one more layer to a picture already strained with improbabilities. When you compile these 7 anomalies together, the mathematical weight becomes substantial. Large size for an interstellar object, forward jet contradicting normal cometary physics, extreme chemical composition with industrial-grade metal separation, color changes without expected molecular signatures, trajectory precisely aligned with our solar system's geometry, arrival timing optimized for planetary encounters, and directional alignment with history's most famous potential SETI signal. Each anomaly has possible natural explanations. Some require special circumstances, others invoke poorly understood chemistry or unusual formation histories, but explanations exist. Science works by finding natural mechanisms for observations, and the scientific community has generally succeeded in constructing plausible natural scenarios for each individual anomaly. The challenge comes from the cumulative probability. If each anomaly has, say, a 10% chance of occurring naturally in an interstellar object, then observing all 7 simultaneously has a probability of roughly 0.1 raised to the 7th power, or about 1 chance in 10 million. Of course, the anomalies might not be fully independent. Some could share common causes or represent different aspects of the same underlying phenomenon, and the individual probabilities are largely educated guesses rather than precisely calculated values. We simply don't have enough examples of interstellar objects to establish reliable statistics. But the exercise illustrates why some scientists began feeling uncomfortable with purely natural explanations. Not because any single observation was impossible to explain, but because the combination required stacking so many low-probability events that the overall scenario became more contrived than some alternatives that had previously seemed absurd. This is where Bayesian reasoning becomes important. Bayesian analysis updates the probability of different hypotheses as new evidence accumulates. If you start with a very low prior probability that interstellar probes exist, say 1 chance in a billion, then even multiple anomalies might not be enough to make artificial origin more likely than natural origin. But if you allow even a small prior probability that technological civilizations might send probes between star systems, perhaps 1 chance in a million, then each anomaly incrementally increases the relative probability of artificial versus natural explanations. Loeb has been explicit about this reasoning. He's stated repeatedly that 3I at LS is most likely a natural comet with unusual but not impossible properties. But he argues that the possibility of artificial origin deserves serious scientific investigation rather than reflexive dismissal, that we should gather as much data as possible using our best instruments, that we should search for any deviations from purely gravitational motion that might indicate propulsion or maneuvering capability, because if there's even a small chance, even a fraction of a percent, that we're witnessing technology from another civilization, the implications are so profound that we have a scientific and perhaps moral obligation to investigate thoroughly. The cost of being wrong in either direction is asymmetric. If we treat it as natural and it's actually artificial, we miss first contact. If we treat it as potentially artificial and it's natural, we learn something interesting about interstellar chemistry. As October 29th approached, and 3I at LS raced toward perihelion, the mathematical relationships that governed its behavior would be pushed to their limits. The power laws describing nickel and cyanogen production, the thermal models predicting surface temperatures, the orbital mechanics governing its trajectory, all would be tested under the extreme conditions of closest solar approach. If the anomalies were simply unusual but natural phenomena, perihelion would likely behave predictably within the bounds of exotic but conventional physics. If they represented something else entirely, something artificial masquerading as natural, then maximum solar energy input might trigger responses that no amount of mathematical rationalization could explain away. The numbers were racing toward their final test, carrying with them the weight of statistical improbability and the possibility that mathematics itself was trying to tell humanity something we weren't quite ready to hear. There's a peculiar moment in Washington when scientific curiosity intersects with national security concerns, when astronomical observations transcend academic interest and land on the desks of people who make decisions about what the public should know. That moment arrived for 3I at LS on October 2nd, Just hours before its closest approach to Mars, in the most unlikely of settings, a routine television interview about government budget negotiations. Stephen Miller, serving as Deputy Chief of Staff for Policy at the White House, was making his scheduled rounds on news programs, explaining the mechanics of the government shutdown that had begun on October 1st. These appearances were standard political theatre, a senior administration official reassuring the public that essential services would continue, that the shutdown was temporary, that responsible adults were working to resolve the budget impasse. But then came a question that seemed to catch Miller slightly off guard. A question that revealed how quickly 3I at LS had escaped the confines of academic astronomy and entered the realm of public discourse that demands political response. Has the president been briefed on the interstellar object 3I at LS? The question hung in the air for just a moment, long enough to suggest that Miller was choosing his words carefully rather than responding with the automatic dismissal you might expect for what should have been a purely scientific matter. His response was measured, diplomatic, crafted with the precision that comes from media training and political experience. He confirmed that appropriate agencies were monitoring the situation. He offered reassurances about the competence and thoroughness of American space programs. He emphasized that there was no danger to Earth, that the object would pass far from our planet. He spoke about the importance of continued investment in NASA and scientific research, but notice what he didn't do. He didn't actually answer whether the president had been briefed. He didn't confirm or deny. He pivoted to broader themes about American scientific capabilities and the importance of maintaining technological leadership. If 3I at LS was simply an interesting but routine astronomical observation, one of thousands made annually by researchers around the world, the expected response would have been straightforward. No, the president hasn't been briefed on individual scientific discoveries. There are thousands of astronomers making observations daily. Presidential briefings cover matters of immediate national importance. But Miller didn't say that. He didn't dismiss the question as inappropriate or irrelevant. Instead, he acknowledged it seriously, used language that suggested ongoing attention from federal agencies, and framed his response in terms that implied 3I at LS had indeed reached levels of government where information management decisions are made. Around the same time, Representative Tim Burchett from Tennessee was making his own television appearances, bringing a different perspective to the growing public conversation about 3I at LS. Burchett serves on the House Committee on Oversight and Accountability, giving him jurisdiction over federal agencies including NASA. He's been particularly vocal about transparency issues, especially regarding unidentified aerial phenomena, pushing for declassification of government files and public disclosure of what agencies know about unexplained objects. What made Burchett's appearance remarkable wasn't just that a sitting congressman was discussing an ongoing astronomical observation. It was that he appeared on screen alongside Avi Loeb, sharing airtime to analyze the implications of the Perseverance images and the broader anomalies surrounding 3I at LS. Congressional representatives don't typically share television panels with astrophysicists to discuss active scientific observations. They appear for political interviews, for policy debates, for responses to breaking news that affects their constituencies. Science communication is usually left to scientists, educators, and specialized journalists. When elected officials join those conversations, it suggests the topic has transcended pure scientific interest and entered territory where political response might be required. Burchett used his platform to advocate for transparency, framing the issue in terms of principle rather than speculation about what 3I at LS might represent. He emphasized that NASA's data belongs to the American people who fund it, that there's no justification for withholding observations of natural phenomena, that government agencies have an obligation to share what they discover with taxpayers who make their work possible. The subtext was unmistakable. Burchett believed information was being withheld, and he was using his position to make it politically uncomfortable for agencies to maintain silence. By appearing alongside Loeb, by lending congressional authority to scientific questions about 3I at LS, he was elevating the discussion beyond academic debate and into the realm of governmental accountability. Representative Anna Paulina Luna from Florida took this political engagement even further. Luna had apparently been briefed on the elongated Perseverance images and found the official explanations insufficient. Rather than accepting standard agency responses, she reached out directly to Avi Loeb, seeking independent expert analysis of the controversial photographs. This direct consultation between a member of Congress and an outside scientist suggests either that Luna wasn't receiving adequate explanations through official channels, or that the explanations she did receive left too many questions unanswered. Either scenario indicates problems with the normal flow of information between agencies and their congressional oversight. Members of Congress receive scientific briefings regularly through established channels. The House Science, Space and Technology Committee maintains relationships with NASA officials. The Congressional Research Service provides detailed analysis of technical issues. When representatives need expert opinions, they typically access them through institutional mechanisms designed to provide authoritative, balanced perspectives. Luna's decision to bypass these channels and seek outside expertise suggests she either couldn't get satisfactory answers through normal procedures, or she suspected that normal procedures might not be providing complete information. Her actions imply a level of institutional distrust that goes beyond typical political skepticism. Luna went even further, sending a formal letter to NASA leadership advocating for the use of the Juno spacecraft, currently in orbit around Jupiter, to study 3I at LS when the comet passes relatively close to Jupiter in March 2026. The letter emphasized the scientific value of such observations, the unique opportunity presented by interstellar objects, the importance of maximizing data collection given their rarity. Letters from congressional representatives to agency heads about specific mission priorities are unusual. Congress sets budgets and provides oversight, but they generally don't micromanage operational decisions about which astronomical targets specific spacecraft should observe. Those choices are typically left to mission scientists, peer review panels, and technical experts who understand instrument capabilities and compete in scientific priorities. Luna's intervention suggests either exceptional constituent pressure, which seems unlikely for such a specialized astronomical topic, or exceptional concern based on information that prompted her to personally advocate for extended observations. The pattern across these political engagements painted a picture of elected officials who were more informed and more concerned about 3I at LS than routine scientific curiosity would warrant. Multiple members of Congress from different committees expressing unusual interest, White House staff being questioned about presidential briefings on astronomical matters, scientists being invited to share platforms with politicians to discuss ongoing observations. This elevation of an interstellar object to the level of political discourse has few precedents in recent history. When the Event Horizon Telescope collaboration released the first image of a black hole in 2019, it generated front-page news and widespread celebration, but no congressional hearings or White House briefings. When scientists detected possible phosphine signatures in Venus's atmosphere in 2020, suggesting potential microbial life, the discovery sparked excitement and debate, but remained within scientific and educational channels. 3I at LS was different, and the difference seemed to center on uncertainty rather than certainty. Black holes and Venus were understood phenomena that confirmed existing theories. 3I at LS was ambiguous, unexplained, open to interpretations that ranged from exotic natural chemistry to possibilities that challenged fundamental assumptions about humanity's place in the universe. There's historical precedent for how governments handle scientific discoveries with ambiguous implications. The SETI protocols developed in the 1980s and updated periodically since provide frameworks for what should happen if potential extraterrestrial intelligence is detected. These aren't binding treaties but guidelines developed through international workshops and conferences, emphasizing verification, caution, and coordination before public announcements. The underlying assumption is that detection of extraterrestrial intelligence represents a species-level event with implications beyond pure science. It requires coordination at governmental levels not to suppress information, but to manage disclosure in ways that minimize panic, misinformation, and international incidents. If observations of 3I at LS had produced data ambiguous enough to potentially suggest artificial origins, even as one remote possibility among several, it would be reasonable for federal agencies to brief elected officials, not to confirm alien technology but to inform them of an anomalous situation where public interest was high and where interpretation remained uncertain. The government shutdown complicated this information management significantly. During normal operations, NASA has dedicated public affairs officers, coordinated communication strategies, established procedures for handling media inquiries. But during shutdowns with skeletal staff, that infrastructure breaks down, scientists are furloughed and can't respond to questions. Press releases don't get drafted. Coordination between agencies falters. Into this communication vacuum, individual scientists began speaking independently, Loeb publishing daily blog posts, other astronomers giving interviews to science journalists, amateur researchers posting analyses on social media platforms. Without central coordination, the narrative fragmented, with multiple interpretations circulating simultaneously, none officially endorsed, all competing for public attention. From a governmental perspective, this decentralized communication created challenges. If you're trying to manage information about an ambiguous situation, uncontrolled messaging from multiple independent sources makes consistency difficult. It becomes harder to maintain coherent responses to media questions. It invites speculation because the absence of official clarity allows theories to flourish unchecked. Some observers suggested the shutdown timing was deliberately convenient, creating plausible deniability for information restrictions. By furloughing NASA staff precisely when 3I at LS data was being collected, the administration could avoid accusations of suppression while still limiting official communication through logistical constraints. But government shutdowns follow predictable political rhythms driven by budget cycles and congressional negotiations. The federal fiscal year ends September 30th, making early October a common time for funding lapses when continuing resolutions fail. The timing coincidence with 3I at LAS's closest approach was almost certainly genuine rather than planned. Still, the coincidence added another layer to a story already heavy with improbable alignments and suspicious synchronicities. Political silence overlapping with technological silence from multiple nations, budget dysfunction disrupting communication exactly when communication was most needed, shutdown procedures preventing transparency precisely when transparency was most desired. Dr. John Brandenburg, a plasma physicist with defense research experience, added his voice to the political dimension through his Blue Planet Red website, where he analyzed 3I at LS, while noting the significance of White House attention to astronomical objects. Brandenburg's track record mixed legitimate scientific credentials with controversial theories about Mars's history, placing him in that ambiguous territory where mainstream expertise intersects with speculative interpretation. His involvement highlighted how 3I at LS was attracting attention across the spectrum of scientific opinion, from conservative mainstream astronomers to researchers who operated at the boundaries of accepted science. The object seemed to serve as a Rorschach test, where different observers saw different implications based on their willingness to consider unconventional possibilities. As October progressed, and 3I at LS approached perihelion, the political attention suggested that whatever happened at closest solar approach would be watched not just by scientists, but by officials responsible for managing information that might have implications beyond academic interest. The questions being asked at high levels of government implied that someone somewhere believed 3I at LS might represent more than routine astronomical observation. Whether that belief was justified or whether it reflected overcautious response to ambiguous data remained to be seen. But the political engagement was real, documentable, and unprecedented in its scope and intensity. When official sources go silent, amateur astronomers have historically stepped into the void with their own telescopes, their own determination, and their own networks for sharing discoveries. This tradition dates back centuries, to William Herschel discovering Uranus from his backyard, to Caroline Herschel cataloguing comets from makeshift observatories, to countless amateur observers who've contributed genuine discoveries to professional astronomy. But the internet age has transformed amateur astronomy from isolated hobbyists sharing findings through postal mail and astronomy club meetings into real-time global networks, where images can be captured in one hemisphere, processed in another, and analyzed worldwide within hours of observation. When 3I at LS made its closest approach to Mars and professional space agencies maintained their coordinated silence, this amateur network activated with unprecedented intensity. People wanted answers, and if official channels wouldn't provide them, they would seek those answers themselves. One of the most controversial contributions came from an observer using the username Dobsonian Power, named after the popular telescope design, favored by many amateur astronomers for its large aperture and relatively simple construction. On October 3rd, as 3I at LS reached its minimum distance from Mars, Dobsonian Power was observing with specialized solar telescope equipment. Using solar telescopes to observe a comet might seem counterintuitive, But 3i at LS's position in the sky was close enough to the Sun from Earth's perspective that conventional nighttime observation had become impossible. Solar telescopes with narrowband filters can detect bright objects near the Sun by blocking most of the overwhelming solar glare, while allowing specific wavelengths to pass through. The image Dobsonian power captured and posted online immediately became a flashpoint of controversy. Heavily processed to bring out faint features, with contrast pushed to maximum levels to reveal any possible structure, it showed what appeared to be a dark, elongated feature against a lighter background. The image quality was poor, grainy, unclear, but it undeniably showed structure of some kind. Within hours, the image had spread across Reddit, Twitter, Facebook, and specialized astronomy forums. Comment sections exploded with interpretations that ranged from careful technical analysis to wild speculation. Some observers saw clear evidence of elongation that vindicated the Perseverance images. Others dismissed it as nothing but noise, artifacts of aggressive image processing, or pareidolia, the human tendency to perceive meaningful patterns in random or ambiguous visual data. Professional astronomers were quick to express skepticism, and their concerns were technically valid. Solar telescopes aren't designed for observing comets, and their optics can introduce distortions that wouldn't appear in instruments designed for deep space observation. The image processing had been so aggressive that distinguishing real signal from enhanced noise became nearly impossible without access to the raw data and detailed knowledge of the processing steps applied. One astronomer noted that when you enhance images aggressively enough, you can make virtually anything appear to have structure. Noise patterns become features. Optical aberrations begin to look like edges and boundaries. The human brain, evolved to recognize patterns for survival, does the rest, connecting dots into shapes, seeing faces in clouds, finding meaning in randomness. But the technical limitations of Dobsonian power's image didn't prevent it from spreading rapidly through social media networks, optimized for engagement rather than accuracy. News outlets picked up the story. YouTube videos appeared analyzing every pixel. Comparisons were made to the Perseverance images, to earlier Hubble photographs, to artistic renderings of what an interstellar probe might look like. More problematically, AI-generated images began appearing online, purporting to show enhanced or clarified versions of 3i at LS. These completely fabricated renderings showed sleek metallic structures with impossible detail, surface features that no telescope could resolve at interstellar distances, artistic interpretations presented as scientific data. The flood of AI-generated content created a secondary information crisis within the primary information vacuum. How do you distinguish genuine amateur observations, flawed but honest attempts to image the object, from sophisticated fabrications designed to generate clicks, views, and ad revenue? Some AI images were obviously fake, showing surface details and structural elements that violated basic physics and optical limitations, but others were more subtle, showing plausible comet-like structures with just enough ambiguity to seem authentic. Meanwhile, more experienced amateur observers were conducting their own observational campaigns with better equipment and more rigorous procedures. Astrophotographers with tracking mounts, telescopes that automatically compensate for Earth's rotation to keep targets centered during long exposures, were producing higher quality images than Dobsonian power's solar telescope attempt. Gerald Raymond and Michael Jager, observing from Namibia during the September 7th total lunar eclipse, had already captured the dramatic color change from red to green that became central to debates about 3i at ELIS's chemical composition. Their images, taken with professional-grade amateur equipment under optimal conditions, showed clear evidence of green emission in the coma surrounding what appeared to be an elongated white core. Other observers in the southern hemisphere, where 3i at LS was better positioned before it disappeared behind the sun, were uploading their results to astronomy forums with detailed technical specifications and processing notes. When properly tracked and imaged with narrowband filters that isolated specific emission lines, 3i at LS consistently appeared to have an extended core surrounded by green emission. The core appeared elongated in many of these better quality images, though not as dramatically as the 4:1 ratio suggested by the Perseverance composites. The elongation looked more like 2:1 or 1.5:1, significant enough to be noticeable, but subtle enough that it could still be explained by various instrumental or processing effects. Was this real structure, or still an artifact? The question became central to online debates that drew in amateur astronomers. professional scientists, image processing experts, and curious observers from around the world. Tracking telescopes compensate for Earth's rotation, but 3i at LS itself was moving against the background stars. If exposure times were long enough, that motion could blur the image, potentially creating elongation in the direction of the object's apparent motion across the sky. But some of the better exposures were relatively short. Under a minute, not long enough for significant motion blur at 3i at Laus's angular velocity. And the elongation appeared consistent across different observers using different equipment in different locations at different times. That consistency suggested either a real structural feature or a systematic effect that all the observers were experiencing similarly. Dr. Horace Drew, posting under his online handle Red Collie, had been particularly active in analyzing and reprocessing amateur images from multiple sources. Drew posted enhanced versions showing the white center and green periphery distribution, arguing that the color pattern supported his interpretation, that the object possessed extended white structure rather than a small nucleus surrounded by green coma. His argument remained geometrically consistent. If you're looking at a small bright nucleus through a large green coma, using instruments that have limited resolution and some degree of atmospheric blurring, you should see a predominantly green blur in the final image. The white shouldn't dominate the center, unless the white emitting region is comparable in size to or larger than the green emitting region. Professional astronomers countered that cometary comas aren't uniformly bright. They're densest near the nucleus and fade with distance according to well-understood physical processes. Even if the coma is extensive and green-tinted, the central brightness from the nucleus can dominate in images, unless exposures are specifically calibrated to bring out faint extended emission at the expense of saturating the core. Most amateur images are optimized to capture the bright central region clearly, which means they're not ideal for studying the distribution of faint outer emission. Seeing white centers with green halos could be an expected result of typical exposure and processing choices, rather than evidence for unusual structure. The back and forth between Drew and other observers illustrated a fundamental challenge in interpreting astronomical images, especially those taken by amateur observers with varying equipment, experience, and processing techniques. Two people looking at identical raw data can produce different processed images that emphasize different features, leading to different interpretations of what the data actually shows. Amateur astronomy forums developed detailed threads analyzing processing techniques, comparing different approaches, attempting to establish best practices for imaging faint objects near the sun. Experienced astrophotographers posted tutorials explaining common artifacts, demonstrating how processing choices affect final results, showing how easy it is to create false structures through over-sharpening or excessive contrast enhancement. They explained how cosmic ray hits on digital camera sensors can create bright spots that might be mistaken for stars or structural features, how diffraction spikes from telescope support structures can appear as linear features extending from bright objects, how atmospheric turbulence can cause apparent elongation or distortion that changes with altitude and seeing conditions. But educational content and careful technical explanations don't generate the same viral engagement as bold claims and sensational interpretations. The algorithms that govern social media distribution prioritize content that generates clicks, shares, and comments over content that provides nuanced understanding or technical accuracy. As a result, the most visible amateur contributions to the 3i at LS conversation weren't necessarily the most reliable or well-informed. Spectacular but questionable images received thousands of shares, while careful analysis by experienced observers remained buried in specialized forums with limited visibility. A website appeared, calling itself an independent research platform dedicated to collecting and analyzing all available images of 3i at LS. The site compiled amateur observations, professional press releases, scientific papers, blog posts, and social media content into what appeared to be a comprehensive resource for understanding the object. But the site treated all sources as equally credible, giving the same weight to rigorous peer-reviewed studies and unsupported speculation. Graphs showing nickel emission rates from the Very Large Telescope appeared alongside AI-generated images of hypothetical spacecraft. Careful spectroscopic analysis was presented next to blurry amateur photographs and artistic interpretations. This mixing of reliable and unreliable sources created an environment where distinguishing accurate information from fiction required expertise that most visitors didn't possess. The site appeared comprehensive and authoritative while actually making the truth harder to discern by drowning verified data in speculation and fabrication. As October progressed and 3I@LS moved closer to the Sun, Earth-based observations became impossible regardless of equipment quality or observer expertise. The angular separation from the Sun decreased below safe observation limits, even for specialized solar telescopes. By mid-October, the object was lost in solar glare from our perspective. The final amateur images captured before solar conjunction showed 3I@LS, brightening as expected, with the coma expanding and the green emission intensifying as solar heating increased outgassing rates. These final observations were consistent with normal cometary behavior, approaching perihelion, but they didn't definitively resolve any of the debates about structure, composition, or the nature of the elongation seen in earlier images. The end of ground-based observation meant that whatever happened at perihelion would be witnessed only by spacecraft positioned to observe the inner solar system. The amateur astronomy community had provided valuable data and maintained public engagement during the information vacuum created by official silence, but their contribution had also illustrated the challenges of extracting reliable scientific conclusions from decentralized observations with varying quality and processing standards. The democratic nature of modern amateur astronomy, where anyone with modest equipment and internet access can contribute to ongoing scientific discussions, had both revealed and complicated the mystery of 3I@LS, leaving more questions than answers as the object disappeared into the glare of our star. October 29th, 2025. A date that would either mark humanity's closest observation of a remarkable natural phenomenon, or the moment when something artificial revealed its true nature under the full intensity of our sun's energy. The difference between these possibilities hung in the balance of physics, mathematics, and the fundamental question of what 3I@LS truly represented. Perihelion for any object is more than just a point on an orbital path. It's a moment of maximum stress, maximum energy input, maximum revelation. For a comet, perihelion represents the climactic point in its journey, when solar radiation reaches peak intensity and drives the most vigorous outgassing the object will ever experience. For something artificial, something designed, perihelion might represent an activation point, a moment when accumulated solar energy reaches levels sufficient to power systems that had remained dormant during billions of years in the cold darkness between stars. The physics was straightforward and unforgiving. Solar radiation follows an inverse square law. At Earth's distance of 1 astronomical unit, we receive about 1,360 watts per square meter. Move to 1.36 AU where 3I@LS would reach perihelion, and that energy density drops to approximately 730 watts per square meter. Still substantial, still enough to drive powerful chemistry and physics, still enough to represent a shock to any object that had spent geological ages in interstellar space, where temperatures hover just degrees above absolute zero. For 3I@LS, this represented an unprecedented thermal assault. Even during its journey through our solar system from beyond Jupiter's orbit inward, it had never experienced this intensity of heating, and if the steep power laws governing its nickel and cyanogen production held true, if those mathematical relationships extrapolated forward as predicted, then perihelion should trigger an eruption of outgassing that would dwarf anything observed during the months of approach. The challenge was that perihelion would occur when Earth couldn't watch. The geometry was cruel in its precision. 3I@LS would pass closest to the Sun when our planet was positioned on the opposite side of our star, with 147 million kilometers of incandescent plasma, blocking any direct observation. No telescope on Earth or in Earth orbit could penetrate that overwhelming glare to see what was happening at the moment of truth. This observational blindness created a peculiar situation for those who suspected 3I@LS might be more than natural. If something were going to happen, if maneuvers were planned or systems were going to activate, the moment of maximum solar energy input, while hidden from Earth's direct surveillance, would be optimal timing. It was either the most frustrating coincidence in astronomical history, or it was intentional design. The Solar and Heliospheric Observatory, positioned at the L1 Lagrange point between Earth and Sun, offered humanity's best hope for perihelion observations. SOHO had been maintaining continuous watch over our star since 1995, its coronagraphs blocking direct sunlight to study the solar corona and detect objects passing through the inner solar system. SOHO's instruments weren't designed for detailed cometary studies, but they were capable of detecting 3I at LS as it passed through the spacecraft's field of view. The LASCO coronagraphs could track the object's brightness, measure its approximate position, document any dramatic changes in its appearance or behavior, but they couldn't resolve structure at the level needed to distinguish a compact nucleus from an extended coma, much less determine shape or detect surface features. Parker Solar Probe presented another observational opportunity. Though its positioning and mission parameters made observations challenging, this NASA spacecraft, launched in 2018 to study the solar corona from unprecedented proximity, follows its own elliptical orbit that brings it within 6 million kilometers of the solar surface, closer than any previous human-made object had ever ventured. Parker's WHISPER instrument, the Wide Field Imager for Solar Probe, has a field of view designed to capture solar wind structures and coronal phenomena. Under optimal circumstances, it might catch glimpses of 3I at LS as the comet passed through the inner solar system, but the spacecraft's trajectory meant any observations would be peripheral, catching the comet in the background of solar physics measurements rather than as a primary target. The European Space Agency's JUICE spacecraft, en route to Jupiter to study the ice moons of the outer solar system, was positioned to provide the best post-perihelion observations. About 2 weeks after 3I at LEL's closest solar approach, when the comet would still be highly active but far enough from the Sun to allow detailed study, JUICE's instruments could capture high-resolution images and spectroscopic data. JUICE carries multiple cameras and spectrometers originally designed for studying icy moons, instruments perfectly suited for analyzing an active comet. The Janus camera system could capture color images with resolution sufficient to reveal structural details. The MAGI spectrometer could analyze chemical composition across visible and infrared wavelengths. The UVS ultraviolet spectrograph could detect gases emitting in UV bands. ESA had confirmed that JUICE would observe 3I at LS starting November 2nd and continuing through late November, emphasizing that this would provide the best views of the comet in its most active state when the tail would be fully developed and brightness would peak. But JUICE observations would come after perihelion, after whatever was going to happen had already occurred. This timing gap created a blind spot at the most critical moment. The detailed, high-resolution observations that could definitively answer questions about structure, nuclear size and shape, outgassing symmetry, and possible artificial characteristics, those observations wouldn't exist for the perihelion moment itself. Ground-based astronomers were completely sidelined. 3I at LS remained lost behind the Sun from Earth's perspective, geometrically impossible to observe regardless of telescope size or technological sophistication. The most powerful observatories on Earth and in Earth orbit were rendered useless by simple orbital mechanics and the overwhelming brightness of our star. Some had noted this observational gap months earlier, when 3I at LS's trajectory was first calculated. Precisely, Avi Loeb had mentioned it in one of his papers, pointing out that the comet would be occulted by the Sun from Earth's perspective during its perihelion passage. If you were planning operations without observation by a particular planet, arranging perihelion to occur when that planet couldn't see you would be strategically optimal. Of course, reading intent into orbital mechanics requires believing the trajectory was designed rather than natural. Gravitational dynamics don't care about observational geometry from Earth. The fact that perihelion happened to occur when Earth couldn't watch was most likely simple chance, a consequence of when 3I at LS entered our solar system and what hyperbolic path it followed under the influence of our Sun's gravity. But the speculation persisted in online discussions and scientific forums. What if 3I at LS planned to use perihelion for a solar Oberth maneuver? The Oberth effect is genuine orbital mechanics. If you have propulsion capability and fire it, when you're deep in a gravity well moving at high velocity, you get more change in kinetic energy than if you use the same propulsion in deep space. It's most efficient to perform major trajectory changes at perihelion, where you're moving fastest and gravitational potential energy can amplify the effects of any thrust you apply. If 3I at LS wanted to change from a hyperbolic escape trajectory to a bound orbit that would keep it in our solar system permanently, the optimal place for that maneuver would be at closest solar approach. And if such a maneuver were timed to occur when Earth couldn't observe it directly, observers would need weeks or months to calculate the new trajectory and realize it had changed. By the time 3I at LS emerged from behind the Sun in December, any orbital modification would be complete. but detecting and confirming the change would require careful astrometric measurements over extended periods.